In this example, we will try to find the density of free electrons in metal using the phenomena that is called the Hall effect. Okay, so for Hall effect, if we are given a slab with current I going past the slab, okay, so when the current I going past, the electrons will be moving on the opposite side of the current. Okay, so and if we give the system the magnetic field that is perpendicular to the slab, the magnetic field will direct the electrons towards one side of the slab, so that electrons will be accumulated on the left hand side. And at the same time, with electrons going in one direction, the hole that has positive charges will be accumulated in the other direction. When the electrons and holes are accumulated on the opposite side, electric field is generated between the two sides. To the left hand side of this. And so that if we are given the x, y, and z coordinates, okay, we are going to have the electric field in y-axis, so we call this EY. Okay, and from this electric field at the distance W, which is the width of this slab, if we try to put on a voltmeter to measure the potential difference between two sides of the slab, there will be the voltage that is called the Hall voltage, or VH. And the phenomena where the newly coming electrons that move towards the one end of the slab is going in the straight line because of the force between the magnetic field, the force due to the magnetic field on the left hand side, and the force to the right hand side by the electric field is equal. So when FB equals to FE like this, the motion of the electron will be along the straight line. So this effect is called the Hall effect. Okay, so we are going to use the Hall effect to find the density of free electrons in the metal. So that is what this system is done for. So when we consider the equilibrium between FB and FE, and we substitute EVB for FB, and for FE it will be charge times by the electric field. So that we have the relationship between the velocity and the B field and the E field. So V is E over B. Okay. Then we come to consider the Hall voltage, or VH. So given the voltage of the constant electric field E, so we have the relationship V equals to ED when D is the distance. So in this case, our voltage or potential difference will be the VH, and the distance that the electric field is W, or the width of the slab. So VH is E times by the W. So that v, or the velocity or the speed of the electrons. Can be written in terms of E divided by B, and also in term of V divided by WB. Well, V is the whole voltage. So that is the relationship that we have. Okay. And then from this speed, or we can say that this is a drift speed. From this equation, so I equals NEVA from chapter 5. So we can use the information to find the N, or the density of free electrons. Okay, in terms of I divided by E electron charge, the drift velocity that we have calculated, and A, or the area. So for A or the area, we are considering this side of the slab. Okay, which has the thickness of T and the width of W. So A is the thickness times by the width. So EV and WT. Okay. Then we just substitute the value of drift velocity, the expression of drift velocity, as VH divided by WB times by WT, and the W or the width can be cancelled, so that we have N as IB and divided by EVH times by the thickness T. And that's the expression for the density. So if I try to substitute all the values, so I, the question given you as 78 ampere, B, it is given as 2.29 Tesla, and then electron charge is 1.6 times 10 to the minus 19 Coulomb. And VH, or the whole voltage, is given by 130 microvolt, or times 10 to the minus 6 volt. And the thickness of 0.23 millimeter, or 0.23 times 10 to the minus 3 meter. So finally, you can use your calculators to evaluate the values of N, and what we get is about 3.73 times 10 to the 28 per cubic meter. So that means the density of the free electron is in 1 cubic meter, that will be this number. It's quite a huge number, so it will be this number of electrons, and that is our answer.